Today we are here with Ronian Xu, author of the book Modern Classical Optical System Design. Ronian has a Bachelor of Science in Optics and a Bachelor of Arts in Physics, both by the University of Rochester. He also has a Master of Science in Optics by the same university. Ronian is an optics consultant with more than 25 years of professional experience designing optical systems. Ronian, what inspired you to write the book Modern Classical Optical System Design?
Hi, Zahar. Yes. Well, I guess a couple of things. First of all, if you look at the college textbooks out there, they're very excellent, of course, and the technical resources books out there, they're very, very good as well. Many of them are written in such a way, and by necessity, written in such a way that the author has to be authoritative in the subject matter, obviously, but the material and therefore the knowledge that is being presented is oftentimes being presented without revealing the struggles that the author had to go through to get to the point of having high knowledge. So I wanted to write a book that reflects my struggle as an author, as an expert in my field, to get there. Because knowledge, if you think about it, knowledge and therefore wisdom is never gained without struggle. You can be born a genius, but not born with wisdom, right? So I wanted the book to kind of reflect that journey, to include segments that talk about how difficult the subject really is. And so if you are a reader and you're trying to understand this material, you're not alone if you're struggling because I struggle through it too. In fact, all authors struggle to get to the knowledge that they have attained in their life and career. So that would be a different kind of book, I think, and it would resonate with readers such as myself who struggle through try to learn material that's actually quite difficult to acquire and to learn. So that's one well I guess one reason, but second reason has to do with something that you and I as kind of touched on briefly in a pre-meeting or before prior to this I guess this interview, which is that I noticed that you're not just uh, a marketer in ILP Publishing, but also a chair of a working group in ILP Publishing on diversity and inclusiveness. And it resonated with me because I'm thinking, well, to me, diversity and inclusivity is I guess not just about diversity of races and ethnicity, sexual orientation, or maybe uh, and any other kind of things that's normally considered, diversity. But there's also a diversity in learning style, a learning method. In a classroom, there's always a population of students and learners with the ability to acquire the knowledge as it is right there in front of them. But there's also a small population of learners who, if you're in a classroom, it's very difficult to follow the material because you're asking yourself why this, why that, before you can move on to the next material. You're trying to piece things together and connect the dots. I wanted to write a book that kind of has that kind of feeling to it. That would be for a population of students like myself who in a classroom may struggle, but when you have a book with you that tells you things about the author struggling through and also tells you about why things are not as obvious as they are, then it can resonate well with the readers and hopefully just kind of nudge you along the way. So these two reasons really um, motivated me to write this book.
Thanks, Ronian. You've already touched a little bit on this, but who is this book intended for?
Oh, okay. Well, that's a nice segue to this question from for the previous question. You're right. So, um, because of the two reasons I mentioned earlier on, it's probably best for early career designers, such as you graduate from college with a bachelor's degree or a master's degree, and now you kind of have all this knowledge, but you may not know how it's really being applied to industry. And that's why That's why this book was really written for. And it could also be for professional engineers who, after a few years in the industry, are wondering, well, where am I going from here? How did I even get here? And what am I going to do with new knowledge that I don't even have? So I think it's good for early career designers, even professionals, and maybe even students in college who, let's say you are a freshman or a sophomore, first or second year, and you're trying to have foresight and look ahead in your studies, and you're going, well, you know what? Um, I'm thinking of being an optical designer, but what exactly is that? So you browse through the library and you maybe come across my book and you go, oh, here's a book that's a lot of advanced material that I may not fully understand or know now, but at least there are segments in the book that tell me what I need to do to get there. So then I'll take this book, I'll put it aside, and then after graduating, I'll take it back again. Okay, now I'm ready to take on the world.
What are the key features and topics that you cover in this book?
Um, Well, this book actually began with having a planned four chapters. It ended up with three because I ran out of time. So the four chapters would was supposed to be imaging, illumination, optical system product development, and then a bunch of advanced material. Now the advanced material has been condensed significantly to an appendix D in the book because as I mentioned, I ran out of time. So, but that doesn't take away from the main course work, I guess you can say. Um, Beginning with imaging. Imaging is because everyone is acquainted with imaging. Lenses are in camera systems; they form images, right? So, um, imaging, and then that moves on towards illumination. Illumination is not so obvious. Lenses not just form images; they can also project rays from a light source to a screen, and produce some kind of distribution of light, and then it moves on towards optical system product development. The basic idea there is that you take imaging knowledge and illumination knowledge, you piece it together, you can create an optical product because all optical products need a scene to be illuminated. If the illumination is available, like the sun is illuminating a scene, then you don't need an illuminator. But in some cases, if you're in a dark room, you need an illuminator. So you need light shining onto it, and then you need a lens to image what you're shining light onto an image sensor, and so on and so forth. Uh, but also optical system product development, it's not something that is touched on in a lot of books. In my book, I also talk about some nuances that you would encounter when you develop an optical product, such as things like stray light, a little bit of stray light, but more so on things like if you pass light through an optical filter, and you tilt the filter, the band pass of the filter will shift. And why is that, right? And many other kinds of nuances. In imaging itself, if you just go back to the first chapter, imaging, it's quite a long, big chapter. In fact, when I was working with the production team of the book, I was asked whether or not I could consider condensing that because it is quite long. Well, it's because in imaging, as I mentioned before, it is the core thing of optics and optical design is really imaging. And in there, some topics that I highlight are things like, well, you know what? If I'm a lens designer, the toughest thing to do in lens design really is to choose glass. How do you select if I've got a system of four or five lenses, all the same material, I can pretty much optimize this lens system to create a nice sharp image of a scene if the scene is illuminated with a single color, like green light, for example. But what happens if I've got white light shining on the scene, like a blue, green, and red rays striking the scene, going through the lens system, and when they bend through the lens system, they will disperse like a rainbow, right? So you get this so-called chromatic aberration in the image. You got this discoloring effect. How do we choose glass? There are theories and everything about how to choose glass for a single or double lens element. But if you're given a multi-lens element, suddenly how do I begin? Where do I begin? And I explain from first principles how that's really done. You take, I have a working example actually a work example that has four elements of lenses, all the same material. Now I need to what's called achromatize. How do we do that? Well, then I explain. Okay, well, you can insert a lens here, and then the reason why that works is because of some first principles, things like that. So these are the kinds of topics that um, I myself have been trying to find in many, many books. You can find some subtleties here and there in existing books. In my book, I want to touch on it directly and say, look, okay, this is how you really, really do it if you're a novice. And then obviously, if you want further material and further details, you can go and look at the other resources that are available to you. Hopefully that answered that question.
Thank you so much. In your opinion, what are the most exciting areas in your field?
Oh, okay. Very excellent question because what is exciting to me may not be exciting to other people, even in my field. So first, I'll begin by talking about what's exciting to me, and then I'll talk about what I think is exciting to other people. That's just not me. All right. So for me, um, the what continues to excite me in optics and optical system design is that there's so much so-called classical material that is already well established with many, many principles in textbooks and even very, very old textbooks in optics that continue to be uncovered or rediscovered or reinterpreted in a different way by different authors. And that's also kind of why my book is called Modern Classical Optical System Design, because um, I'm taking old principles and looking at it from a new way, a new perspective. And I'm not the only ones doing it. There are other authors every now and then who publish this material in journal articles, and it's very exciting because you get to see things done differently, and you can apply them differently in a new way and create new products, for example. So that's to me that's very exciting. But outside of that, nowadays in the commercial world of optics, people talk about things like augmented reality, mixed reality, and virtual reality, AR, MR, AR, VR, MR, I guess, mixed reality. This is wearing goggles with special optics, and you look through the goggles, you can see the world in a different way. Augmented reality is wearing goggles, looking at the outside world, and then uh, electronics and optics will augment the scene, which means it will add to the scene certain kind of details that the outside world it does not have. So that you can apply that to games, you can apply it to video games and other kinds of maybe robotics as well. That's exciting for a lot of people. I'm not involved in that one, in that application, but other people are all really into it. And then there's something called meta optics, META, meta optics. It doesn't have to do with Facebook. It's meta optics, as in is a material that is artificial, and it is made by it's very thin. It has a lot of nanoparticles arranged in some way that can manipulate and bend rays through them and focus it in different ways. And it's finding applications in mobile phones, maybe even small micro lenses or microscope objective lenses, and perhaps many other applications we do not know about. So I talked about AR, MR, VR. I talked about meta optics. There's also computational optics. Computational optics is things like, well, you form an image on a camera. Now you can manipulate the image digitally or in real time. One example is extending the depth of focus or depth of field of an optical system. You can do it by various means and by manipulating light using for example, a free-form optical component or an A-sphere. It's called an A-sphere. You put it into your lens camera system such that it blurs out the image, but it blurs out the image the same way no matter how far the object is or how close the object is. So it's invariant. The image is invariant. And all you do after that is you take the image that you form and then you perform a computational step called deconvolution, which extracts the original sharp image. and you can do it for a range of distances. So there's computational and computational optics also diverts into computational imaging and computational illumination. So these three fields, augmented reality, meta optics, computational optics, are quite exciting right now in the area of optical system design.
What are you working currently on?
Oh, currently, um, I focus a lot of my time on a lot of research and development for my employer, Venture Bio, Venture Biotech Modules Business, VBMB. Um, I spend most of my time consulting for this company, where a bunch of us are pretty much inventing and developing various kinds of products. And my role in this company is the design and development of very special little illumination systems. It's actually a little module. We call it a module, a little illumination system that can provide very, very even illumination onto a screen. We call it a Veluminator, as an illuminator with a V in there, Veluminator. So these Veluminators can be used for all kinds of applications, like projection, for example, or microscopy. I know I'm doing a little bit of selling here, on this note. And if for those who are dialed in or not dialed in, but watching this interview, if you go to https://v-bmb, that's it, v-bmb.com. That's the company that I'm working for currently, and I'm the one responsible for the illumination modules there. If you look at the YouTube videos there and look at the white papers I've written there, they describe these very, very special illumination modules that produce very, very even, flat top, very flat illumination for various applications. So I'm spending a lot of my time doing that. Obviously, I don't talk about that in my book because of the patents and the kind of secrecy that's involved in the technology. But it's very exciting for me. And moving forward, my role is to develop even more applications in that area, and also to focus on the technological aspects of that product.
Why do you think an early career researcher should move into this field?
Wow, very excellent question. The the reasons that I have moved into this field are can be somewhat different from the reasons I think um, early career designers should move into this field. For me, I moved into this field when I was 11 years old. When I was 11, for some reason, I got interested in astronomy. And then I got interested because astronomy uses telescopes and optical instruments, spectroscopes. I got interested in that. And that is related to optics. So that got me into this optics thing. And I'm into it because I just love it. It's fascinating to me. Light is everywhere. So if I wanted to experiment with my ideas, I could just buy a simple flashlight from a store, turn it on, and that's my light source. I can just, if I need lenses, I can go to Toys R Us, or I can go and to another bookstore and buy some very cheap magnifying glasses, and I can just experiment with the light. I mean, I can go outside because and cast a shadow, right? Create a pinhole camera because outside a light source is the sun. So light is everywhere. I can do so much with it, and it just fascinates me. But luckily for me, that also got me my very nice job today as a consultant. Obviously, I have to work through many, many, many years in a company, but um, having having this experience and this knowledge in optics gave me a really good job, with a good pay. So this kind of segues into why I think early career or undergraduates should get into this field, because there is a good amount of job security in this as well. If you go to Indeed.com or Indeed anywhere in the world, you'll see, and if you just try to search for an- the job optical engineer or optical designer, you'll find that it's really quite pervasive. So I think that there's good job security there, and nowadays people talk about AI. taking over the world or taking over jobs. Artificial intelligence will never take over your job if you're an optical system designer. Never, because uh, if you well one way to look at it is that if you were to search Chat GPT or some AI for some optical solution, doing that if you are not an optical engineer is similar to me Googling for how to fix my kitchen faucet when I should actually call a plumber, an expert to do it. You could always search for solutions from an artificial intelligence source for optics. But if you do not possess the knowledge and skill and experience as an optical system designer to design optical systems and to solve optical problems, you will never really get the solution you want by just searching an artificial intelligence program. So I think there's a good amount of job security there. The work is good. The pay is also good. Um, and you get into this very unique position where not a lot of people can do what you can do, and therefore the demand would be there. And you have always the opportunity to choose between going towards maintaining your employment as an engineer in a company, or I've seen many optical designers like myself who have branched off and decided to be independent, to be a consultant. Some of them being consultant even only after 10 years or less than that, maybe even 8 years, 6 years, because they become really good in what they do by focusing on the optical design. And when you're good enough, they can just say, you know what, I'm just going to be independent, be a consultant, and then find my own path that way. So I think it's a very exciting field. It's got good job security. Robots will not take over your job, and I think it's a field that more people should get into.
That is great. Thank you so much for your time, Ronian.
Thank you so much, Azahar. I appreciate it. Thank you for having me.